Hi students, welcome back to geology. Today we are talking about extreme weather. So this is part of your atmosphere, seasons, and weather module. The first thing we need to understand is what the difference between weather and climate is. A lot of times these are used interchangeably, but they are technically not the same. So any state of the atmosphere, whether it's cold or hot, or wet, or dry, or stormy, or cloudy, all of those conditions are considered weather. Okay, and this all involves the troposphere. So it's all happening in the troposphere, which we talked about in the last lecture. And then with climate, this is going to be the state of the atmosphere over time. So these long periods of time, long trends and patterns that we see within our weather. So knowing that the climate is warming over time, not just that it's a warm day versus a cold day. Okay, so weather is like saying tomorrow it's going to be cold. Climate is saying the last 5 years have been relatively warmer than the previous 5 years. Right, so the first thing we need to talk about is states of matter. So most of us are pretty familiar with solids, liquids, and gases. There's also plasmas, which we will talk about later this lecture when we talk about lightning. So this is any gas that carries an electrical charge. And then there's some definitions there for you for solid, liquid, and gas. And the big thing here is knowing how we get from one state to another. So this is this change of state of the material. So melting, obviously, is going to be something going from solid state to liquid state. Freezing is liquid to solid. Evaporation is when a liquid boils and changes into a gas, so evaporation from the surface. And then we also see deposition, which will be water vapor that can change into snowflakes and fall as snow. And then sublimation is a transition of a solid phase to a gas phase with the passing of liquid. So we don't even get to the liquid phase. We just bypass it when we go from a solid to a gas through sublimation. So think of like dry ice. Dry ice doesn't necessarily melt, but it does sublimate and it goes straight into a gas from the solid state. All right, so precipitation can come in a lot of different forms. We see rain and drizzle. We see freezing rain. We have a couple freezing rains on there. We have sleet. We have snow, hail. All of these different things can come down as precipitation, right? So most of us are usually just rain or snow, but there's other things that can happen, like hail, if you've ever experienced. Those are usually lumps of ice that fall from cumulonimbus clouds. This happens sometimes in Fresno. I think it happened last year, 2022. We had a couple of instances where there was some smaller size hail that came down and it kind of blanketed Fresno, and there were some areas that looked like it had snowed, but it was really just hail. And then there's sleet and freezing rain, which happens when raindrops either freeze before they hit the ground or they freeze when they hit the ground. So they generally start as rain, but then they tend to freeze at some point in time between the clouds and the ground or on the ground. All right, then looking at some cloud types. So these are the 4 basic cloud types, and with severe storms, we see kind of some combination of the cumulus and the nimbus. But in general, these are some of the clouds that you might see in the sky. Cirrus clouds are the thin, wispy clouds that you see, and they generally contain a lot of ice crystals rather than water droplets, which makes them really thin. Then we have stratus clouds, which are like a dense blanket-looking cloud. The nimbus clouds are dark, doom and gloom looking clouds that are usually associated with thunderstorms and lightning. And then cumulus clouds are usually the big puffy kind of cotton ball-y looking clouds that you'll see. So cumulus clouds mean that you're going to have mostly good weather. Cirrus clouds means you're going to have relatively good weather. Stratus clouds are going to be rain and warm weather and snow and cold weather. And then your nimbus clouds, you're looking at a storm. So how does weather work, right? So how does all this stuff move? The biggest thing that we need to look at is convection. So we've talked about convection before within the mantle that helps drive plate tectonics, but here we're looking at convection of heat and air, right? So as air gets closer to the surface of the earth, it is warmed, right? The earth is fairly warm. And so the air that's closer to the earth is going to be warmer than the air that's further from the surface. And so the air that is warm tends to become less dense, it expands, and that material, that air starts to float upwards because of its density. And so it comes up to the top of the air column. And then that air starts to cool down, it condenses, and then it becomes more dense and it falls. And so we get this cycling of air, and as that cycling of air happens and there's different convective cells interacting with each other, that helps drive all of the changes in pressure, the changes in temperature, and then the storm systems that we see. Okay, so you've probably heard of high pressure systems and low pressure systems if you've ever watched the Weather Channel or the news. The Weather Channel beats this into you, understanding high pressure and low pressure systems. But high pressure systems, like you see on the left hand side there, is when cooler air is sinking. So this is that cold air that was at the top. It is sinking because of its density, right? And it is warmed. So as it gets closer to the surface, it becomes more warm and it can hold more moisture for a longer period of time, which means that it's going to be mostly sunny skies. So in a high pressure situation, we're going to see sunny skies and maybe some clouds, but no, not necessarily any precipitation. With a low pressure system, it's warm air rising and becoming cold, and cold air cannot hold moisture very well. And so what happens is that water tends to precipitate from those clouds that are formed in that scenario because the cold air just cannot hold on to that moisture. And so you tend to see a lot of rain in a low pressure system or some sort of precipitation in a low pressure system. So when you see a big L over the map, that's a low pressure system, and that is going to generate weather, storms. If you see a big H over the map on the weather map when you're watching maybe the Weather Channel or the news, that means that you're going to have clear skies and it's going to be a pretty nice day. Or it's going to be really hot in Fresno. So weather comes from the west. So this is how we can predict weather. We can predict weather for a certain number of days. I know they give out 14-day forecasts, but sometimes those, as you probably noticed, change very quickly, just depending on what happens. Especially in California, we are susceptible to the ocean, right? So whatever is happening over the ocean, it could either disappear really quickly or change really quickly and create a storm. So everything is coming from the west, and so you can look to the west on a map and kind of tell what kind of weather you would expect in a few days. So whatever's happening west of you is generally coming your direction, and so predictions in the middle of a landmass are a lot easier than when you're looking at a coastal situation. All right, and that weather is also coming from fronts and air masses that are kind of our standards, especially in the United States, for what we tend to see. So within air masses, we see continents, maritime or oceans, and then whether it's coming from the poles or the tropics. So with a continental polar air mass, we're going to get cold and dry. So the cold is coming from the polar region, so it's coming from like the North Pole, and the dry is coming from continent. So continent is dry, polar is cold. Continental tropical is going to be hot and dry. So again, continent is dry and tropical is hot. Okay. Then with maritime polar, we're looking at cool and moist. So polar is cold and maritime, which is over the oceans, is going to be moist. And then we have maritime tropical, which is going to be warm and moist because maritime is going to be moist. So ocean, moist, excuse me. And then tropical coming from the equator is going to be warm. Okay. And this map shows you where all of those are coming from and how they are interacting. And so where air masses meet are where we're going to see fronts. So there's a various amount of fronts. We have cold fronts, warm fronts, and then we have some combination occluded fronts and stationary fronts. And so this is where those air masses that I just showed you are meeting, and then they're going to create our storm systems. Okay, so let's look at warm fronts first. So warm front is when warm air is replacing cold air. And so you have new warm air coming in, It's going to replace that cold air and push it out. And generally what we see is a small slope or a shallow slope, and that air just gets pushed out and the warm air goes up. It can hold the moisture for much longer, so we tend to have light precipitation to maybe moderate, just depending on the amount of water molecules in the atmosphere. And on a map, you would see it as a line with red semicircles. And you'll notice, so in the bottom right-hand corner there, you'll notice the direction of the front's movement. Behind it will be higher temperatures, and on the other side will be colder temperatures. And that shows you the warm front progressing. On the contrary, cold fronts are much more aggressive. So this is where cold air is replacing warm air. And generally we see this on a map with a line and some blue triangles. And again, we see cold air on the side that is progressing forward, and then warm air on the opposite side. And so this is about twice as steep as warm fronts. It moves much quicker and is much more violent. So we end up with a lot of intense precipitation. And sometimes that duration is a lot shorter because cold air, like we said, does not hold moisture well. So it'll dump all of the precipitation very quickly. And generally what happens is after an intense rain, we tend to see clear skies after that point, which is nice, but it can cause a lot of damage in a short period of time. So yeah. And we have stationary fronts, which is when a cold front and a warm front meet, and there's no progression either direction. And so there's kind of like this pause. These don't usually last very long. And eventually, when it starts moving again, it will become either a cold or a warm front again. All right, and then we look at an occluded front, which is going to be a combination of the two fronts. This is the most damaging. And so as you see in this diagram here, we have a cold front moving forward, and it runs into a warm front there. And when it runs into that warm front, we have all of this warm air going up, and then it's being replaced by all cold air on both sides. And so we get really heavy precipitation, we get large thunderstorms, and on a map, you would see this as, depending on the progression of the occluded front when it's on the map, you might see a warm air front on one side and then the cold air front, and then when they meet, it is pink, and then it's a combination of the symbols. So other symbols you might see on a map are these. All of these will tell you something about what's happening in the particular area, but they will also obviously verbally tell you. But if you just happen to see the map, this is what you're looking at for the symbols. All right, so then we're going to lastly look at some storm systems here: thunderstorms, tornadoes, hurricanes, and blizzards. All right, first up is thunderstorms. So these are coming from cumulonimbus clouds. Remember, that's a combination of the two, cumulus and nimbus clouds. We're going to see heavy rainfall, lightning, and maybe some hail. So the hail and the lightning has been common in thunderstorms here. And there are 2,000 in progress at any one time on Earth. We see 100,000 plus per year in the United States. And Florida and the Gulf Coast region get the most. So how does thunder and lightning work? Everybody always wants to know, right? So remember, lightning is that plasma state that we were talking about. So what happens here is there is a charge difference between the clouds and the ground. And so when there's a charge difference, there's going to be an interaction, or there could be a spark. So, right, you think about walking on carpet and you're dragging your feet. Or when you wear flip-flops, this happens to me all the time. I'm wearing sandals or flip-flops and I'm dragging my feet on the ground and I go to touch something, there is a spark because I've just charged myself, right? So I've made myself look like that cloud where I'm positively charged, and I interacted with something that was negatively charged or less charged than I was. And that's what happens between the clouds and the ground. We have positively charged clouds, and we have a negatively or much less charged ground. And that interaction creates that spark. So it's just like when you touch something and you shock yourself. But this is a much bigger scale, obviously, and it can be much more intense. So Thunder is then the result of the lightning. So the lightning occurs and then the thunder makes the sound. And depending on how close you are to the lightning, it will obviously take longer between when the lightning happens and the thunder occur and you hear the thunder. And there's also going to be a change in the type of sound, whether you hear a clap or you might hear a rumbling. So you can kind of figure out how close you are to the lightning depending on how far apart the events are and then what the type of sound you hear. So remember, light travels faster than sound, so that's why you don't necessarily hear them together unless you are right where it's happening. And trust me, you do not want to be right where it's happening, but that's why there's a delay. And so the further the delay gets, or the bigger the delay gets, then you know it's kind of moving away from you and you're not necessarily really close to it. All right, then moving on to tornadoes. So tornadoes are oftentimes a lot shorter duration than a lot of people anticipate, although they can cause a lot of damage in a very short amount of time. But this is a rotating column of air from a cumulonimbus cloud. Those clouds are just terrible clouds. They can create a lot of crazy weather. There's usually low pressure inside, and the winds can get up to 300 miles per hour, which is crazy. We do see an average of 770 each year in the United States. They're most frequent from April to June, so kind of in the spring, early summer months. They're oftentimes associated with thunderstorms, and their exact cause, what really causes them to start, is really unknown. We see like little tiny ones every once in a while, but they're mostly derived from like dust and wind at the surface and don't always connect to the clouds. In the Central Valley, we see those every once in a while, but we don't see these massive tornadoes like they do in the Midwest. Depending on the wind speed and the amount of damage they're causing, tornadoes are put on a scale from 0 to 5, and this is called the Fujita scale. It was developed in 1971 to try to describe tornadoes and kind of give them a classification. So when somebody says we were in an F5 tornado, you know what they're talking about. All right, and then hurricanes. Hurricanes are one of the most damaging natural disasters on Earth. They are formed from a large, swirling, low-pressure system that forms over tropical oceans and then comes onto land and causes destruction. If they go over additional tropical oceans, they can pick up intensity, and that's what caused Hurricane Katrina in 2005 to be so devastating. And I'll show you that in just a second. So we are looking at speeds up to 250 kilometers per hour, and they must exceed 119 kilometers per hour to be considered a hurricane, and they have to be moving in a cyclonic circulation. They oftentimes are found between 5 and 20 degrees latitude, so they're pretty close to the equator. We don't see them much farther north or much farther south. So they're very tropical storms. And for hurricanes, we use the Saffir-Simpson scale, which was developed in 1969 to try to help scale hurricanes. So this is category 1 to 5. Again, we're depending on the effects or the damage and the winds to classify them. And like I said, hurricanes can increase in intensity and decrease in intensity during their travels. So the reason that Hurricane Katrina was so devastating was because when it was off the coast of Florida, it was closer to a 2 or 3 category, and it passed through Florida, lost some intensity. They thought they were in the clear, but in the Gulf of Mexico, it picked up more warm ocean water, increased in intensity, and got much closer to a category 5 by the time it hit New Orleans. And so they were very devastated by Hurricane Katrina, and they tend to be devastated by multiple hurricanes that hit them every year. All right, then last here we have a blizzard, which we are not familiar with in the Central Valley. We're not familiar with hurricanes either. But this is going to be a winter storm that has strong winds, cold temperatures, low visibility, and technically lasts more than 3 hours. So instead of it just being a snowstorm or a winter storm, once it lasts more than 3 hours, we consider it a blizzard. And so, as you've probably noticed, in the Central Valley, we don't really have to deal with many of these things. Thunderstorms are the closest. Hail is the closest thing we really deal with. All of these other storm systems, we're pretty safe from. So although it is hot in the Central Valley, we don't have to deal with a lot of these other severe weather things. And then lastly here, we have the severe weather safety. So we have the National Weather Service that issues out watches and warnings that help prepare people for severe weather. And the difference between a watch and a warning, it depends on whether there are favorable conditions or the conditions already exist. So if there's favorable conditions, it's a watch. If the conditions exist, it's a warning. And so the people that issue these are meteorologists. They study and predict weather. If you are ever curious more about weather, we have Sean Boyd, which is a wonderful weatherman on our teaching roster here in geography. So if you have questions, you can feel free to ask him, or I can put you in contact with him. He's great. All right, so in summary, we have air masses and fronts that create weather that we see and experience. Weather comes from the west. Our pressure systems help indicate what weather conditions we're going to see, and the National Weather Service sends out our warnings and our watches. All right, that's it for this lecture. I will see you guys in the next one. Bye.